So I'm Gil Tene. I'm the CTO and one of the co-founders of Azul Systems. And I'm also one of the Java Community Process Executive Committee members. As Jakub said, we had our 2-day face-to-face meeting here in Prague. We just finished this afternoon, and we were hosted by T-Mobile here. So thanks for T-Mobile as well. As some of you may know, the Java Community Process has an executive committee that is made up of a lot of companies, some of them ratified and some of them elected by the community. Azul is one of the elected companies, so you and everybody else in the JCP elected us to the seat. And the executive committee is really responsible for advising and steering the process itself, the rules, and approving JSRs, allowing JSRs, carrying them through the process all the way to maturity and standardization. I think over the years the JCP has done really great things. We all, I assume a lot of you use Java because you're in a Java community user group, so this is always a result of all this effort. And we meet several times a year, but we only meet face-to-face 3 or 4 times. And every year we choose different places to go. Usually there's 1 or 2 in the United States. But this year we came here, and this is my first time in Prague, so beautiful city. And thanks for having us here. I'll start with the garbage collection talk, and later, because I think 2 or 3 more of the people are on the way here. So later, if you have questions about the Java community process, what we do, specific questions about what we're trying to add, change, improve, we'll talk about it at the end of the talk. Okay? Good. Just a second. Okay, so this is a talk about garbage collection, and if you use Java, you probably know about garbage collection. Not a happy thing that you know about it, but you probably do. So here's what we're going to try to cover in this talk and achieve. The first is that this is about education. I want you to understand what the collectors do. I want you to understand terminology and metrics and mechanisms. I'm not going to tell you how to set the right value for 25 different flags. That's not what we're going to talk about. We're going to do much more important things, and that's to talk about how the machine that is the garbage collector works, not just for a specific garbage collector, but in general. And then after that, once you understand how the machine works, for you to use your brain to figure out better or understand better how to deal with garbage collection in environments that you run in. And that should help you a lot if you're not already an expert in understanding what controls you have, what the trade-offs are, and what happens. You learn enough to understand, enough to do dangerous things, and you know, all of us being programmers, that's what we have to do. But you're not going to become an overnight expert. There's a lot of actual experience that you'll need. And one last thing. I'm from Azul Systems, and we make a very interesting and very good JVM. So I promise that I will not talk to you about how great our JVM is and why we have the best garbage collector on earth until very late in this talk. The reason is that I need you to be able to understand why we're the best garbage collectors, so I'll educate you about how garbage collectors work, and then we'll look at that. Specifically, I am going to use what we talked today to classify collectors with actual precise terms, explaining what mechanisms are and what mechanisms are used by what parts of which collectors. And when we get to the end, hopefully, you'll be able to recognize the different classifications. Okay, so a little bit about me. I've been working on garbage collectors and JVMs for about a decade now. I've been working with virtual machines. Hi, Patrick. So as I said, some of our members are trickling in. We said we'll do the JCP part at the end. Yeah. So I've been working on garbage collectors for about a decade now and using managed runtimes virtual machines for about 20 years. This is a picture of me working on garbage collecting. This is actually a trash compactor, really a trash compactor, and it's in my kitchen. It wasn't working right, so I opened it up and worked on it some. And I figured it'd be funny to take the garbage collector handbook and use it there. But more seriously, I've created and published 2 key garbage collection algorithms in the last 6 years now, Pauseless and C4. And I've also built everything from operating systems and device drivers and virtual machines and firewalls and switches and management systems for millions of people that ran in Java on top of a lot of different things. So I've built a lot of parts of the overall system. I like to say that somewhere between sand and a nationwide telephone system is different parts that I've played with. Azul basically makes scalable Java virtual machines. That's what we do for a living. We've had the approach of doing whatever is necessary to make a scalable Java virtual machine, and we've been doing this for 10 years. So whatever is necessary included some very interesting, crazy things. Like we built our own hardware. We built our own chips. We designed 864-way symmetric multiprocessor machines with a 1/4 terabyte of memory. That's the architecture up there. And we delivered 3 generations of these. But we don't do those anymore. We don't design new Vega machines, which is our architecture. And that's because as of about 3.5 years ago, the roadmap for commodity servers made it clear that we do not have to build our own hardware anymore. We can take what we've built and move it to software-only x86 platforms. And that's really what Azul does today. A product called Zing. It's a JVM for Linux, and we'll talk about it at the end. As I said, we do garbage collection. We are probably best known for that, but there are other things like elastic memory and virtualization that we also do. And we also run mission-critical environments across the globe. A lot of people run bet-the-business applications. These are just samples of some of them. So that's enough about me and enough about Azul. Here's what we're going to cover step by step. We're going to start with fundamentals and key mechanisms of garbage collection. We'll do some terminology and metrics, define specific terms and metrics that are interesting. We're going to classify actual collectors that you can use today using the terms, the mechanisms, and the metrics that we talked about. And then I'm going to talk about a problem I call the application memory wall. And then I'm going to talk about something that solves it. So before we start with that, I'm going to ask you guys a simple poll question. I ask this question in almost every audience I have where there are more than 10 people. And the question is really simple. You all run Java. How big is the Java heap that you run or use in current applications? Do you have an application that uses more than ½ gigabyte of Java heap? If you do, raise your hand. That's most of you. Really? None of you have more than ½ gigabyte? Raise the other hand. Okay. How about more than 1 gigabyte? Okay, still most of you. More than 2 gigabytes? Okay, still a few, but a little less. More than 4? Look around. Okay. More than 10? I see there's 1, 2. Now you guys are brave. More than 20? Okay, there. Okay, so as you can see, the guess I had, I didn't change this for the presentation, is that somewhere around here is where almost everybody is, and above that, there'll be a few people that actually run larger heaps. Remember this, because we're going to get back to it when we talk about the problems here. So, why should you care about garbage collection? Partly what you just saw is one of the key reasons, but I like to use an example, a real-world example of why understanding how garbage collectors work is important for people who write software in Java. And I like to call this the story of the good little architect. This really happened, and it happened to us about 6 years ago, 5, 6 years ago. A good architect, as opposed to just a good developer, is somebody who first of all can make everybody do what they want. They can make an entire team follow an architecture. If they're good at architecture but they can't do that, they're not an architect, they're a philosopher. Okay? So this is a story of a good architect who can make an entire team what they want, do what they want. And very early when we started building our large memory pauseless JVMs, we ran into an application that had an 18-second pause, which to us was, how can this even happen? So we dug into it, and we found out that every time we ran a collection, the application was doing tens of millions of objects finalizations on every GC cycle we were doing. There were objects being finalized all the time. And by the way, we were doing stop the world finalization, so since then we don't do that anymore. We run that concurrently too, but at the time that's what the pause was. So we went to figure out why is this application finalizing so much. When we dug into it, we saw that every class written in the project over a course of almost 2 years had a finalizer. Every single one of the classes they wrote. There was a really good architect. Okay? Can anybody here guess what the finalizer was doing? Exactly. It was putting nulls in all the fields before the object goes away. It was doing it to help the garbage collector. So most of you probably already know that that's the wrong thing to do. If you don't, then here, you learned something already. But this is not a way to help a garbage collector. It's a way to make the garbage collector do the worst possible thing and really, really slow it down. But this is exactly the right way you would design a C++ application. If you're writing in C++ and you want good discipline, no memory leaks, good memory management, you would make sure that before any object goes away, you destroy everything so that other objects can go away. And you take a lot of care for that, so you have destructors. And if you came from that background, this is exactly the right architecture. On Java, it's exactly the wrong architecture. If you have a garbage collector, this is the worst thing you could do to it. Okay? So this is just an example of why. And by the time we're done, you'll probably understand some of the why this is wrong. So trying to solve garbage collection problems in the application, for example, by putting a finalizer in every class, is dangerous. If you don't understand exactly what you're doing, you could get hurt. And you probably shouldn't do it without understanding or without really seeing what's going on. And you can get very good at it. It is possible to program in heap-friendly ways and ways that make the collector happy. But you should do this only if necessary, only if there are no other choices, only after you've gotten rid of the other inefficiencies in your system. You can get very good at this. You can make applications that allocate nothing. You can make applications that the collectors would be very happy with. However, the hard thing to do is use other people's software when you've gotten that good. Because your code might be very good, but look around you. Does everybody in this room write software that good? And what about all the libraries that you really like? What about the XML parsers and the app servers that actually do allocate objects? Are you going to stop using them? So in Java, you really don't have a choice but to live with how the ecosystem works. You can do very interesting things to solve specific problems. These are all examples of ways of getting around garbage collection pain. Whether it's object pooling, which is sometimes right, mostly not. Things like off-heap storage, which for very specific problems like caching can help. Or things like distributed heaps and chunking things into tiny little pieces. All these are ways to get around issues of memory. And if you do build them, you better be ready to spend a lot of time building them, because at the end you will be building a garbage collector. Okay? You're just moving it to another place. Okay, so last thing before we get into actual mechanisms and metrics. Most people know things about garbage collection. Know this because they believe it or because people have told them that. And I find most of what people know is wrong. Sometimes it's wrong in a way that is, Java is much better than you think. Garbage collection is much better than you think. Sometimes it's the opposite. So for example, garbage collection is extremely efficient. It is faster to allocate objects and let the collector have them than it is to do malloc. Faster by a lot, not by a little. About 3 times less instructions spent and fewer cycles spent and better prefetching capability. It is literally faster to run with a garbage collector as long as you're in the efficient range of its memory configuration. The other part that is important, we just ran through an example of it, is dead objects cost us absolutely nothing to collect. The collectors, and this is all collectors for all current server JVMs and client JVMs as well almost, do not spend any cycles thinking about a dead object. We don't even look at them. So there's no need to do stuff about them, and especially don't need to go there and before it dies, let's clean up. We're not going to visit it if it's dead. And we will absolutely, every commercial JVM today will absolutely find all the dead objects. You don't need to help them. You don't have to make sure that you don't have circular linked lists. The collector is good enough that it doesn't matter what your data structure looks like. If it's dead, we'll find it. If it's live, we'll find it. So these are all important things. They don't exist in non-precise environments, and I'll define precise in a little while. On the other hand, there are many things about garbage collection that are much worse than what people think. Biggest one is, most people think that when something big happens and there's a pause, it's their fault. And it's just because they didn't tune the system right and they didn't write the code right. The reality is, on most JVMs, there will be about 1 second of pause per gigabyte of live data. And there's nothing you'll be able to do about it except make it happen less often. You may be able to change when, but you will not change if. Now, for some people, changing when means I make it so it happens once every 3 days and I reboot every night so it never happens. But you can't make it run forever without this in most systems. There's always an exception. The other one is that if you don't have if you use the garbage collection, that doesn't mean you can't leak memory. You can still have bugs where you keep things alive and they grow and they grow and they grow. That's still a bug. There are a lot fewer causes of memory leaks, but they certainly exist. And this last one is very important. When you had a problem and you worked hard and you got rid of the problem and it was a garbage collection problem, most likely you didn't get rid of it. Most likely what you did is you were running a test for 20 minutes and it didn't work. It failed. So you tuned it and it still didn't work. And you tuned it and it got better but still didn't work. And after a day of tuning, it ran for 20 minutes without seeing a big bad garbage collection. You just moved it to minute 21. That's what mostly happens when you tune things. So unfortunately, long-lived stable behaviors require a lot of testing because most of your tuning moves the problems around, not gets rid of them. Okay, so that's that. Now we're going to get to actual terminology. So why do we define terminology? Let's start with an example. How many here know what a concurrent garbage collector is? Raise your hand. Okay, not that many, or maybe you just don't want to say. How many know what a parallel garbage collector is? They sound very similar. I define them because it's important to define terms. A concurrent collector is a collector that runs while your application is running. It does its job and you keep running at the same time. It's concurrent with your application. A parallel garbage collector is a collector that uses more than one thread. You can be concurrent but not parallel. You can be parallel but not concurrent. You can be concurrent and parallel. Most concurrent collectors are also parallel. And you can be neither one. You could be just single-threaded stop the world. Stop the world is the opposite of concurrent. In the word, you understand. You stop the world, you do the stuff, and then you let it go. Concurrent is exactly the opposite of that. Incremental, which is a name that you'll see more and more often in the coming years, an incremental collector is a collector that takes work that needs to happen, some chunk of work, like collecting your entire heap, and breaks that work into pieces that could be done in increments, usually stop the world increments. So I won't stop you for the whole time. I'll stop you for a little while, and then do some work, and then I'll let you run. It's safe to run now. Then I'll stop you again, and then again. So the increments, incremental collectors are usually about taking a big problem and slicing into smaller times, usually the same amount or even larger amounts of work, but trying to make the individual stops shorter. Now, the last and very important term that I like to define is the word mostly. It's a simple word. Mostly means mostly. Mostly means not always, not all the time. When you see the word mostly, yes? Not all collectors. Concurrent collectors do not. Well, practically is a very good point. So mostly is a word that you'll find about collectors saying, I'm mostly concurrent. I'm mostly parallel. I'm mostly incremental. When you see the word mostly, you should understand that means sometimes I am not concurrent, or sometimes I'm not incremental. Okay? It's most of the time I can, but sometimes not, and you're going to see the sometimes. Mostly is a very important word in classification. Okay, so let's talk some more terms. Precise versus conservative. A collector is conservative when the collector doesn't really know where all the pointers are. And we call it a conservative collector because it has to assume that some things are pointers because it's not sure if they are. Here's a word in memory. That looks like a memory address. I don't know if it's an integer that happens to have that value or an actual memory address. So a conservative collector will, one, it will keep those things alive if there happens to be something there. But more importantly, there's certain things it can't do. A collector is precise if the collector does know where every pointer in memory is, where every pointer in every register is, whenever it needs to do work. A precise collector has some very important qualities. One of the key qualities is that in order to move an object from one place to another, the collector has to be precise. Why? Because if I move an object from one place to another, I need to find the 3 billion pointers that might be pointing to that object. And I need to fix them so they won't point here and they'll point there. What if I found an integer that looks like that pointer? If I changed a value that you have in your program because I moved an object from one place to another, I'll create a very interesting and very rare and hard to detect bug. So that's why you have to know if it's a pointer or not. Once you know it, you can do good things like compact memory, copying memory, and other things we'll talk about here. So precise collectors are necessary for relocating objects. The interesting thing is that from a collector perspective, that's not hard. All the collector needs is somebody to tell it where all the pointers are. That somebody is usually the compiler. And really what makes JIT compilers and Java virtual machines different in compilation work and complexity and how good the compiler has to be is the fact that not only does the compiler need to generate good code, it needs to generate a description for the collector for every place you might stop in the code, telling it exactly where the references are, which register and which stack location has what register in it. The heap is easy. We understand types and we now understand, where the references are in an object. But as I'm running alone in the code and I stopped here, where are the references in my registers and stack? The compiler actually generates that information for every possible place in the code that might stop to garbage collect. It's very dense. All commercial JVMs are precise collectors today. Every single one of them. So they're classified as precise. And every single one of them uses a moving collector. Objects will move from point A to point B and they will fix pointers at some point in the run, actually very often for most of them. So I talked about this preciseness and the fact that the compilers tell us where all the things are. Well, they can't really do that for every instruction because some instructions they didn't generate. They might be hand-coded assembly or GCC made it or a library like libc. So we have what we call safe points. Safe points are places in the code where we have the description. We are precise. And the collector can deal with threads and the content of their references when they are at a safe point. And outside of it, it doesn't know where the references are. Not exactly. So a safe point is a place, a GC safe point is a place or a range of execution where as long as we're at the safe point, we know where all the references are for that thread. Okay? There are other types of safe points. I use GC safe point and save point interchangeably, but there are save points that have information beyond garbage collector. So for example, if you want to de-optimize code because you loaded a class and you need to throw away the compiled code and replace it with other code, you need to know not just where all the references are, you need to know where all the integers are and which ones they are and how to change the structure from this frame to that frame. It's a lot more information. So GC save points are just a type of save point, but usually it's the most commonly used save point. So bringing a thread to a save point means somehow I got the thread to be in this state where I know where all the references are. Okay, it sounds like I'm picking my words, but it's important to understand that a thread could be at a save point in running. A thread could be at a save point and use CPU. All it means to be at a save point is I can't go past the point where I know where all the references are. The most common case where you are at a save point but running is native calls. Every time you go into JNI calls, if you run in there and run in a C loop for a second and come back, the entire second you are at a save point because we knew where all the Java references are even though you're running. You just can't get back and change where they are. So JNI calls are an example of long-lived CPU spending save points. Save point opportunities need to be very dense in the code. They need to happen so that when I want a thread to get to a save point, it'll happen immediately, as in microseconds. If it's not, if it will take a long time to get to a save point, then as all the threads have gotten there, and you're waiting for something we call a global save point, which is bring them all to the state so a collector can run, everybody's waiting for that one guy to get to the save point. So if the save points take a long time, you can get very large pauses, even though it appears that they were still running. Okay, so we talked about precise collectors, we talked about save points. Let's talk about things that are common to all GC mechanisms, all precise GC mechanisms. So every one of them will do this. They'll somehow identify the live objects, what is alive, and they'll all find all the live objects. They will somehow reclaim the dead stuff. That's pretty much what a garbage collector has to do. It has to find the garbage and collect it. And this third thing that they all will do is at some point it will move an object from one place to another. Every precise collector does this, mostly because it doesn't need to be precise if it isn't doing the third case, but it's also because it's not practical to run in modern environments without doing all three. Examples of this: mark, sweep, compact. That's a mechanism used for all generation collectors. Does these three steps: 1, 2, 3. Mark is find all the live stuff. Sweep is let's find all the dead stuff and somehow recoup it. And compact is, oh, the dead stuff comes in little holes and I don't have room for some objects, so move everything around so I'll have a large space for my objects. Mark, sweep, compact. A copying collector, which is a collector used in the young generation, doesn't do mark, sweep, compact. It says, okay, all the live objects are here. Let's move all the live objects there. And now here is empty. It does all these steps as one thing. The copy identifies the live objects. The fact that you copied everything out identified all the dead stuff because you don't have to look for it. And you obviously moved objects. So all these are one pass. But every collector will do all three of these. So let's break it into pieces and define what a mark is. This is not that much text. So a mark, also known as a trace, start from what we call the roots. The roots are usually static variables and threads. And it finds all the references that it can find in the roots. And for every reference, it will follow the reference and look at the object that's pointed to. And say, okay, that's alive. And then look inside the object and follow every reference there. And on and on and on. It basically paints the world through the references. Anything it can reach, it will paint alive. Okay? So if I can get to it from a static variable or thread, it's alive. If I can't get to it, it's not alive. So basically at the end of a mark pass, anything I didn't mark as live is dead. This is why you don't need to help the collector with circular things that are not reachable. If I can't reach the circle, it doesn't matter if there are pointers inside. I'm never going to get to any pointer in there. And if I can reach the circle, then that's really a live thing. It doesn't matter if it's a circle. Complexity. The work for marking is generally linear to the live set of memory. The larger your live set, the more objects you have alive, the longer it takes to find all of them. That's intuitive. Okay? Sweep. Sweep is that next phase in Mark Sweep Compact. Not all collectors do this, but when you do, it's pretty simple. You start at the beginning of the heap, and you scan and look at all the objects, and if it was marked alive, it's alive. If it's not, oh, it's dead. I need to recoup it. So you put it on some list, usually some free lists, either by object size or just a list. So you find all the dead stuff, and now you can reuse them for allocation later. Simple, right? The work to do sweep is linear not to the live set, but to the size of the heap. For the same amount of live data, if I double the heap, I've doubled the cost of sweeping, because I have to visit everything. Mark, I didn't double anything, it's just how much I have alive. Compact. Compact basically deals with the fact that objects get fragmented over time. We will have empty stuff, but it will be holes in otherwise live things. And the problem is that once you run long enough and the heap gets Swiss cheesed and fragmented, you need to allocate one object, and there's a lot of empty room, but there's no room big enough for that one object. You can have half the memory empty, but I don't have room for my 10 kilobyte array. The way you deal with that is you move the objects around so the empty stuff will get bigger and contiguous and defragment it, much like you do to disks and other things. So compaction does two things. One of them is it moves the object. We call that relocating the objects, relocate. It does another thing, and that's to fix all the pointers to the objects that were moved. And we call that remap. So changing the references is a different thing. And of these two, the remap is a lot more work than a relocate. Statistically, in our experience, about 5 times as much work. So a remap scan has to cover every reference in the heap that could possibly point to what was moved. If I move one object, I still need to visit all the pointers that could point to it. It could be 3 billion things that I need to visit just to move one object. Which is why when you compact, usually you compact a lot of things. You do as much as you can so that at least the visits will cover a lot of different work. Complexity, even though it's a complex operation, it's linear to live set, not to memory size, not to heap size. Okay? Good. So we covered mark, sweep, and compact. Let's talk about copy. I described it pretty simply. A copying collector has a from space and a to space. It takes everything that is alive in the from and moves it to the to, and at the end it knows the from is empty. So it's a pretty simple thing. You start from the roots. Anything you find that's in the from, you move there, and anything it can reach, you move there, and when you're done, basically all the objects are in the to, and there's nothing in the from. We freed up a bunch of memory. It's very simple. It's a single pass, and it's pretty efficient. Its work is linear to live set, not to the heap size. It is a relocating thing where the remapping is not as complex as it is in Mark Compact because of that, or Mark Sweep Compact. Okay, so some notes about comparing these mechanisms. Mark Sweep Compact and the rest. Copying has a little problem. If I'm going to copy things from here to there, not knowing how much is alive or dead at the time, I need there to be as big as here. So I need twice as much memory as I have live things, or as I filled up so far. I don't know if it's alive, because it might all be alive and I have to be able to complete. I can't, in a copying collector, you usually can't say, oh, I copied half, but I can't keep copying. It can't stop in the middle, usually. That's, by the way, a term called monolithic that I have not described before. You have to do it all at once, monolithic, as opposed to incremental. Mark Compact typically also requires that same amount, but it doesn't have a correctness problem. It could stop halfway in the middle if there's no more room, so it's not monolithic. It just won't be able to do compaction of an entire heap in one cycle if there's not enough memory for it. Both of these they need more headroom and empty memory, but Mark Sweep Compact can do it in place. It's an efficiency benefit. Copy and Mark Compact are linear only to the live set, but Mark Sweep Compact is also linear to the heap size. Okay, so as far as how much time it'll take and how much work it is, they're different. And then Mark Sweep and sometimes Compact, which is actually a common thing, may be able to avoid some moving work every once in a while. The CMS collector is a good example of that. It's mostly Mark Sweep, sometimes Compact. So copying is typically monolithic, as I explained. So before we start putting these together, let's talk about another mechanism, generational collection. How many of you know what a generational collector is? Okay, a lot, because you pretty much have to use one. So generational collection is based on a very simple observation. It's called the generational hypothesis, and that is the observation that most of the objects we allocate die very soon after we allocate them. They're temporary. Most of what we make is temporary. That is not the same as most of the objects that are alive are young. It's actually the opposite. So not everything dies at once, just most. And if we use that knowledge and we focus garbage collection only on the recently allocated stuff, and we're somehow able to only deal with that part, we know a very important thing about it. It's very sparse. I have this much heap, and statistically I know that I have very little alive in it. Most of it is dead, it's young. And that means that I can use a collector that is efficient when that relationship exists. A copying collector is linear to the live set, not to the size of what you're scanning. So if I have a heap, a new generation this big, but only this much live, all I do is move the this much live away and I'm done. I collected all that. The larger the ratio between the size of the generation and the live part, the more efficient the collector becomes. It's a great benefit from an efficiency perspective. Oh, what's going on there? Okay, so we collect what do we do with things that are not young? Well, we have to take the young things that stick around and are still alive, at least after a while. We have to push them somewhere else. We have to put them in a place where we're not focusing that young collector. The reason we have to do that is if we don't, we're no longer looking at recently allocated objects. We'll have a lot of live stuff and all this efficiency will go away. We have to move them somewhere else or we will lose efficiency. We'll lose the basic thing that makes this work. So every once in a while we'll collect the other thing too. When it fills up, the old generation or whatever people call it, the 10-year generation, eventually you're going to have to deal with it. But you can filter very well on the way to it. You tend to get about an order of magnitude or more. Often we see 20x improvement in efficiency on generational versus exactly the same thing without generational on the same amount of memory. So this is an extremely valuable thing we get to do with garbage collectors. Now how does this work? So how do we collect only a little part and don't look outside? Well, we use something we call a remembered set. Remember how I said a collector starts with roots and follows and does everything, and when it's done, it's done? Well, a remembered set is additional roots for the young generation. In addition to the stacks, in addition to the static variables, anything in the old generation that points to the young generation, that's a root for the young generation. So we don't just start from the stacks and the threads, we also know about all these pointers from the old to the young, and we also start from there. And that means that if we got all the roots into the young, I can legitimately do collection only of the young. Remembered sets are necessary for generational collection. You can't do generational without them. Some form of remembered set. So literally the collector knows about any place outside of the young generation that might point into the young generation. It's more complex than just safe points and just preciseness. The nice thing about generational collection is we get to use a copying collector, which is very efficient, but we don't need 2x the memory. Because we're only doing the young generational with a copying collector. And if we say, okay, here's the young generation, here's the little place I'm trying to stuff it into. This is the survivor space. So I do it, and most of the time it works, but what if there's more live stuff than in the size of the survivor space? What if I just loaded a gigabyte into memory and it hasn't died yet because I'm reading stuff from a file? Well, if it was just a copying collector, I'd have to crash. But since this is a copying collector in the young generation, all I have to do is say, well, I need room, I'll just put it in the old generation. It's premature promotion, but it works. So it's safe, it's correct, it can run. And as long as you are mostly fitting in the survivor spaces, you don't have to do that. Usually you want to make sure that the surviving objects remain in the young generation long enough to die there, but not too long to become old and have to work on them a lot. So I said before I won't give you flags, but if there's one thing to learn about this is immediate promotion can dramatically reduce the efficiency of young generation. But never promoting will also dramatically reduce the efficiency of it. So there's this room in between where you want to be. You don't want to be promoting immediately, because then things that are about to die, you actually move to the old generation and lost the filter on. But if you keep everything there, you have no filter at all. Okay. How does this remembered set work? Well, we have to know about all the pointers. So how do we track them? Well, every store of every reference to memory has to figure out or track the potential fact that it is pointing into the young generation. So mostly, well, mostly, no, not that kind of mostly, usually, there's some form of doing this, a very popular form. All the commercial JVMs I know have used this form, is what we call card marking. For every area of memory that might have a pointer to the young generation, we have something, a bit or a byte, that says, you need to look there when you're scanning the routes. And what we do is every time we store a reference that needs tracking, we also set the bit on the appropriate thing so we know to visit that again. There are variations of this. There's a write barrier on every store of every reference to memory. The JIT compilers have to correctly generate that on every store of every reference. And in Hotspot, for example, that card mark is 1 byte for every 512 bytes in memory. Some other collectors like Azul's use a more precise card mark. We have 1 bit for every word. And the difference there is if you're precise, then you don't have to scan the area and look for pointers. You know exactly which pointer it is, but it takes a little more space. There's other issues with whether you're conservative or not. So for example, Hotspot will simply write a bit on every time it writes. It doesn't even check to see whether this is a pointer from new to old or not. But filtering techniques that say only store if you are a pointer from old to new but not for the other combinations make for a cleaner card mark. They also make the code slower because you have to do more work in the write barrier, but there's a trade-off there. So this is how this stuff works. At this point I'm going to pause a little bit and see if there are any questions so far, because now we're going to start looking at the combinations of collectors and how they're put together. Everything clear so far? Good. Touché. Okay. So here are the typical combinations you'll find in garbage collectors in commercial environments. The young generation is usually in copying collector. Why? Because it's so efficient. The young generation is usually monolithic, meaning once you start copying, it has to be able to finish, and usually stop the world monolithic. So that pause will finish. There's no incremental to it. Okay? I say usually because there's an example, an academic paper from about 4 years ago from IBM on a real-time collector that has an incremental copying collector for the young generation. So, but not in a commercially shipping one. The old generation is usually mark sweep compact. It could be any of these. It could be stop the world, it could be concurrent, it could be mostly concurrent, it could be incremental stop the world, or mostly incremental stop the world. Hopefully, you now mostly understand what most of those words are. So this is, when you look at collectors and classify them, you look at what is the young generation behavior, what is the old generation behavior, well, assuming it's generational, but they all are. Okay, here are more terms. I'm not going to explain all of them, okay? We don't have that much time. But important ones to understand, by the way, mutator up there is what we call you guys. Mutator is the application. It's the one that mutates and changes the graph of the heap. The collector treats that as the only thing that changes the world. So when collector people talk about a mutator, they're really talking about the application. Monolithic stop the world is a very important term. And as you saw in classification, it pops up a lot. These are metrics. Again, I'm not going to cover all of them, but later, if you want to look at the slides, look at them. It's important to look at each one and see if you understand what it means. But within that, allocation rate is a very important metric. How fast are you allocating memory? The collector needs to be able to keep up with that or spend time with it. And why is it important? Because it generally is the best indicator of your throughput. Not knowing what your application does, I pretty much guarantee that if it does 100 times a second and allocates 50 megabytes per second, if you do 200 per second, it'll allocate 100 megabytes a second. It's linear to your work. Allocation is a side effect of your work. I actually like to say that the job of a CPU is to generate garbage, and a side effect of that is your work. It's not the other way around. Mutation rate, the rate at which you're changing the shape of the heap. You can change the shape of the heap without allocating. Every time you store a reference anywhere in the heap, you're mutating the heap. And again, that rate tends to be linear to how fast your application runs. If you double your speed, if you do 10 times as much per second as before, mutation rate will probably be 10 times as much per second with it. So both of these track your work rate very closely. Collectors that work at certain allocation rates and not at others will work at certain application throughputs as not at others. Or will keep their behavior within certain scales but break at those above those. Marking time is probably obvious, and compaction time, probably the biggest pause you will see in any collector, is very important. How long does it take to compact whatever I'm compacting, the whole heap, an increment, or whatever it is? So let's play around a little more, get you a little more intuition. Empty memory and CPU, there's interesting trade-offs between the two. And it's really easy to explain 2 points on this, on a graph here. The first one is, if I had exactly 1 byte of empty memory in a gigabyte of data, all the time. So if I allocate 1 byte, some other byte got freed before I allocate it, right? If that happened, the collector would be pretty inefficient. Every time you allocate a byte, I have to somehow scan a gigabyte and find a dead thing in it. That's a lot of work. So you pretty much know that you'll spend all your time, all your CPU on garbage collection. That's an intuitive 1-point edge. The other intuitive point is even easier. If you had infinite memory, you would never have to garbage collect. 0% CPU, right? Here's the interesting thing. Between those 2 points, there's an almost perfect 1/x graph of efficiency. Extreme inefficiency and extreme efficiency. Every time you double the amount of empty memory, you double the efficiency of collectors that are either copying or mark compact. Things that are linear to the live set double in efficiency every time you increase the empty memory. It's your #1 knob for efficiency on a machine. You're copying, your young generation collector is almost always a copying collector or mark compact in combination like ours. And growing the amount of empty memory means that I grow the efficiency. Now logically, why does that happen? So the amount of empty memory is basically determining how often I need to collect. So I'm allocating at a certain rate. When I run out of empty memory, I have to collect. The amount of work I do when I collect is not linear to how much memory I had. It's linear to how much alive. It's fixed. So I have a fixed amount of work to do as often as I run out of memory. So increasing the amount of empty memory increases the space between fixed size collections, ultimately bringing you down from 20% to 10% to 5% to 2.5% until you don't care anymore. So the efficiency is very strong there. It is a very powerful tool. Growing the young generation has this effect, not growing the entire heap on Mark Sweep Compact. But you know, it's a very powerful tool. It's why you should not be running at 90%, 99%, 85% utilization of a heap and allocating fast at the same time, because you'll have bad efficiency. And You just need to double the empty memory, not the heap, and you'll double the efficiency. Again, if there's a tip to have, it's there. So we control efficiency with this, right? So it's a great tuning knob. And most people will use it that way. Unfortunately, it also controls the frequency of the pauses. Unfortunately. I mean, it's a good thing, right? It doesn't control how big they are. So this is the way, when you tune for efficiency, this is the way you're hiding the bad thing, right? There's a bad thing. It didn't go away. It's the old generation collector. You have to do it eventually. If you make the young generation more efficient, it moved from having to do it every minute to every 2 to every 4 to, but it's not gone away. You can't run for a year or a week or often a day without facing it. So the big bad thing is just moved forward. So empty memory is a very good tuning knob, not for pause time, for efficiency. If you don't like the amount of CPU you're spending on GC, this is the knob for you. If you don't like the pause length that you run every once in a while because you crash when it happens, this won't save it. Okay, a few tricks on non-stop the world things. So far I talked about efficiency, about pauses, sizes, generational. Stop the world is a problem. And it's a big problem, so people have worked on getting around it. Concurrent marking, finding the live stuff without stopping the world is an interesting challenge. If the world is stopped, marking is very easy, right? You just follow the pointers, live is live, dead is dead, you're done. The problem with concurrent marking is that the object graph is mutating or changing while we're doing it. And there's a classic race, a single race that has to be solved for concurrent marking to work. As the collector is painting, finding the live objects, you, the mutator, could take an object I haven't seen yet, take a reference to it and put it in a place I've already visited, and then get rid of the reference there. The object is still alive, but if the marker completed its pass and didn't notice this, we will crash you. We will collect the live object, which is a really bad thing to do. So we have to plug that up. Everybody doing any form of concurrent marking has to plug that up. A common, simple technique for plugging it up is track all the mutations as they happen. So mark. Anything that changes while it's happening, we track it somewhere. When we're done with the mark pass, we go and say, okay, what changed? And we mark those. Well, you could do that, stop the world, but if you want to stay concurrent, well, anything that changes, we track. So we finish that in what changed. Now that does work pretty well, mostly. It works as long as your mutation rate isn't too big. At a point where you mutate references faster than the collector can follow them, it'll never finish marking. If it's fast and it does catch up, but hey, you know, it takes half an hour, you're still going to run out of empty memory before it gets it to you. So it's a good technique, but it's throughput limited. A modern x86 core will allocate ½ gigabyte per second in normal workloads. It will mutate a dramatic amount of references per second in normal workloads. As long as they don't do a lot of work, it's really easy to follow them concurrently. But if you have a 24 virtual core machine mutating and allocating, it's really hard to keep up with it with this technique. So you may fail, mostly. Well, mostly you'll run and sometimes you fail. The other one is incremental compaction. I'm going to run through this very quick because I want to get to the rest of the points quickly. But basically it's saying, instead of concurrent stuff on compaction, let's try and break the big compaction part where I have to remap 3 billion pointers into parts, into pieces. And we break the memory into regions and we track which region points to which other region. So we have these inter-region remembered sets, kind of like generational but times 100 or 1,000. And we track that this megabyte has 22 other megabytes pointing to it, but the rest of the 1,000 don't. And this one has these, and this one has those. So we track that. And that turns to not be that hard, because we have a write bearer for generational collection anyway. So when we're done, actually the marker can do that pretty well, even without the write bearer. The concurrent marker is the one that uses the write bearer. So when we're done with all this, we can analyze this and say, I can find some number of these things where if I compacted them, I would only have to visit some superset of things that point to them. And the collector will actually look for sets of regions that have common things pointing to them for that efficiency. So one region might have 20 and another region might have 20. If these two overlap and it's only 22 together, then that's efficient. If they don't, you don't get anything for it. So you find a set and you estimate the amount of time it takes to remap all the pointers and all those things that point into it. And if it's small enough for your increment, you do that. And then you're safe because you moved stuff and you fixed all the pointers. It's okay to let you run. There are no wrong pointers. Then we do the next increment and the next increment. This works pretty well. This is what the garbage first collector does. This is what the balanced collector from IBM with J9 does. But it has a slight and important problem. It has an n-square complexity. The number of things that point into a megabyte of heap grows linearly with the heap. The number of things in the heap grows linearly with the heap. That's n squared, the number of regions in it. So while it allows you to contain the work per increment, the amount of increment works that you do will grow with the square of the heap generally. So it's good up to a certain point, but then scale is a problem. So those are examples of things people do about stop the world. If you take a step back, you'll see that over the last, well, since Java started, we do all these things that basically are aimed at delaying the big, bad, eventual, I have to move everything and remap everything pause. So we start with delay tactics like find the empty, easy space, which is generational collection. And that works great, but eventually I have to collect the old generation. It's a lot more efficient, it happens less often. The bad thing doesn't happen every 10 seconds, only every few minutes, but it's still there. Then we had CMS, concurrent mark sweep. It said, okay, we have generational, and then the old generation will do mark sweep. We won't compact. And that'll last for a while until it gets fragmented, but eventually it'll get fragmented and we have to compact. Then we have things like G1 and balanced, very recent in the last year, that say, okay, I have to compact. Can I compact only parts so that the pause isn't as big as an entire heap? And that does work, mostly. Eventually, you're going to have to deal with the popular objects you're not dealing with. Eventually, you're going to have to deal with the complexity problem. These are all delays or effective ways of making the bad thing happen less often as we make computers bigger and faster. But we're falling behind as an industry. So let's use everything we talked about and classify the collectors you have. I told you that collectors usually fall into these categories. So let's look at them. The most popular collector on Earth for Java is the hotspot parallel GC algorithm. Why is it the most popular collector? Because it's the default collector. If you say nothing, that's what's going to run. So now it's also the most efficient collector. Classification-wise, it uses a monolithic stop-the-world copying new-gen collector. You should now understand every word in that sentence. Okay? It also uses a monolithic stop-the-world mark sweep compact all generation. Both of these are parallel. Not concurrent, parallel. It used to be that only the first one was parallel. But we have parallel all gen as of the most recent things as the default setting. Okay, that's parallel GC, simple. So CMS, concurrent mark sweep, that's the flag you use to -XX plus use mark sweep GC. It's a concurrent mark sweep collector. If you read the academic paper, it says it's a mostly concurrent mark sweep collector. So let's classify it. What kind of generational new gen collector do you think it has? A monolithic stop the world copying new gen collector. The word concurrent doesn't show up anywhere in here. The CMS part only talks about the old generation. Here's the old generation. It's a mostly concurrent, non-compacting old generation. Has a mostly concurrent marker. It has that multi-pass marker we talked about. As long as throughput is there, it'll work. It has a tiny catch-up stop the world, but that's noise. It has a truly concurrent sweeper. Not mostly, but always concurrent if it's sweeping. But it doesn't compact. So how does it do that? Well, this is how it does that. It's mostly concurrent mark sweep, except for when it has to compact, and then it's a full stop the world monolithic mark sweep compact. Okay? So that's concurrent mark sweep. G1, GC, and this is the same classification as the balanced collector from IBM as well. And to some degree, the JRocket concurrent compactors and deterministic collectors fall into this category, but there's not enough of public information about them that I feel comfortable classifying them as this. Monolithic, stop the world, copying new gen. A mostly concurrent old gen marker. It's slightly different in implementation than CMS, but not in a way that matters here. Okay? Same technique, multipass. It has a stop the world, not concurrent, mostly incremental, compacting old gen. Mostly incremental because most of the time it can do increments. But if you get popular objects, if every 1 megabyte region has one object that is very popular, you're going to have to compact the whole heap in one big thing, not an increment. It has a fallback, because it's mostly, to a full stop the world mark sweep compact. Okay? Fallback. Okay, so that was classification of the common ones you can get your hands on mostly today. Let's talk about this application memory wall I promised you, and then we'll quickly go to solution 2. What is this application memory wall? Well, remember this. So I predicted that you will fall mostly into that range. What's the problem with that? Well, the problem is, well, how many of you program for servers? Okay. This is what a server looks like in 2012. These are list prices off of the Dell website in the United States from a couple months ago. It's even cheaper now. So a commodity low-end server that goes in a rack will have around 100 gigabytes of memory in it. You guys don't really use a server. You run on one, but you don't really care if it's got half of that, a tenth of that. It's so much bigger than your application. So you fill it up with a lot of little things. And by the way, I mean, this is moving at Moore's law. So memory is extremely cheap, as in it costs less than $1 per gigabyte per month to have memory. Okay, so it's not expensive. And we can actually get to it in extreme bandwidths. All these modern cores and CPUs and chips are very, very good at this. That's what a server is. The application memory wall is simply an observation of the mismatch between the previous two slides. For whatever reason, for some reason, application instances seem to not be able to use the capacity of servers today. Not directly. It takes a lot of instances to use a little server. And the problem is not static. It's moving at Moore's law. Every year this gets worse. So let's look at this from a point of view of, wait, who cares? Maybe nobody needs more than that, right? So a common question is, right? So hopefully we understand that that's not real. And history is kind of against that number. But is there a right number? Right now, you guys are somewhere in between this number and that number, moving at what? Moore's law? There is no right number. The right number is, you know, moving around by how cheap stuff is. And by the way, Bill Gates did not actually say that quote. At least he says he didn't say it. The target is just right for a point in time. When 640K looked like this huge amount of memory people won't use for the next decade, that sounded like a smart thing to say. It's just history makes you think twice before you say that again. A way to look at this over time is to define what I call a tiny application. A tiny application is that application that you would not distribute, or if you did distribute into lots of little pieces, you wouldn't be proud of it. You wouldn't tell your friends about it. And we can look at how big that is over time. I actually remember back to the 1980s. And I ran stuff on a VAX 11 780s back then, and you could get a quarter or half megabyte server in an apartment. It cost $200,000, and you can run a 100 kilobyte program on that. You didn't have to break it into pieces, but if you had a megabyte, well, no, that didn't fit in a computer. So you broke it into pieces. 10 years later, a 10 megabyte problem was tiny. I could get somebody to buy me a workstation or a server that had 32 meg of memory, and I could just solve it there. Didn't have to break it into pieces, but if I had a gigabyte, well, yeah, that's a farm of machines. 10 years later, the web was built on the back of 1 gigabyte WebLogic heaps, running on 2 to 4 gigabyte servers. This is where we are today. That server costs less than any of the other configurations on that in absolute dollars and in inflation-adjusted dollars. What is the tiny application that you should be embarrassed telling people you do before you break it into pieces? It would seem like it should be around 100 gigabytes, but most of you were not ashamed to say 1 or 2 gigabytes, so that changed. This is how we actually progressed. And that's what the application memory wall looks like. Okay? It's a problem and it's getting worse, and now we're at a JVM is 1/20th or 1/40th of a server, and next year it's going to be worse and worse and worse. It's already silly to talk about it as silly as 640K was in 1989 or 1990. So what's causing it? Garbage collection. Why? Because applications pause, and when they pause, if the pause is big because the memory is big, you just don't build that application. There's an acceptable level of response time, and you don't like the fact that it stops for a second or 2 or 3, but you can't handle the fact that it stops for a minute or 2 or 3, so you don't build ones that stop for that length. And we are already at a point where at current 2, 3, 4, 6 gigabyte kind of things, JVMs will pause for multiple seconds, so that's where people stop. The root cause is a link between scale and responsiveness. That's why we don't grow memory. That's why we don't use servers to their fullest. And it's not any of these. It's not efficiency. It's not how much resources we use, because we have all these resources that are not being used. It's not about speed. The common transaction in Java is really fast, except for when it freezes and it does nothing for a while. It's not about the minor GCs for most people, because it's the big bad one that breaks and you can't, handle that. That's the problem. It's also not about how often the big bad ones happen. It's the fact that they happen. Does it matter if you crash every 5 minutes or every 20 minutes? Are you going to ship that? Probably not. People don't like to ship or build broken systems, so they basically avoid it, and they avoid using the memory that causes the breakage. That's the root cause and link between these. So what's the problem? What are the problems we need to solve to get rid of that? Well, these are what servers look like, right? And monolithic stop the world operation is the cause for why we don't use servers to their fullest, and we're an embarrassing 20x, 30x, and growing problem here. So how do we handle that? Well, one way to handle that is this. I got this slide from Kirk Pepperdine, by the way. I use it for a lot of different things. I just changed the label at the top. But this is a way to deal with it. Don't tell me it exists. Or, nah, it's noise. So here's an example technique of doing that. Let's map response time, run a 2,000-second test. Oh, that looks great. Okay? But if you expand it, you see that, yeah, there's this blip every once in a while. That must have been some noise. I don't know, an electric grid blip, or I don't know what it was, right? If you back up and you look at a day, you see that it happens extremely regularly, every hour or certain minutes and all that. And as long as you didn't look at that, you were happy, right? But that's the real world you're in, if you actually have pauses that size. So that was one way to handle it. Another way is what I call creative language. Well, let's rename the problem and make it sound good. This is an example quote from marketing materials of a JVM. We will guarantee you a worst case of X milliseconds 99% of the time. Literally, this JVM said 5 millisecond worst case, 99% of the time. Let me explain to you what that actually says. An hour has 3,600 seconds in it. 1% of an hour is 36 seconds. I can do that and pause for 36 seconds once an hour, and I'm still doing it. So marketing's good. But reality still has the pause. You use the word mostly. Mostly is a way to handle the problem. Just make it sound good. And what mostly means is the opposite of the good thing that follows it. Sometimes the bad thing will happen. That's what mostly means. Another thing is to say stuff like fairly consistent or nice. Fairly consistent means it'll sometimes be terrible in consistency. Okay? It doesn't mean consistent. Typical pauses are in the tens of milliseconds. Again, I'm quoting from actual material. That actually means some pauses will be a lot bigger than 10 milliseconds. I told you, right? It's just, you read the nice thing and you go on. So these are ways to handle it and ignore it. It's just other ways to bury your hands in the sand. But another way to handle it is to actually measure stuff. And we built a little tool that we open source. In fact, I put it in the public domain, so you can do whatever you want with it. And it does things like this. It measures the behavior of the system. Now, it doesn't measure your application. It measures the computer, the JVM and everything under it, and whether it could run it all. And it records it. Those are hiccups, what I call hiccups. And the way hiccups, the idea in hiccups is that response time doesn't look just like this. This is a 40-year-old chart from IBM that says, you know, response time as you grow the load will get worse. That's true. But what do we mean by response time? Are we talking about the average or the mean or the max or percentiles? You actually want to know how each one of them behaves. And do we really think that response time is a function of load? It is to some degree. But here's an actual graph from something I downloaded from the web. I don't know what the test really did. But it does have nice labels. It has an active user count, so it shows growing load, and it has the response time here, the black line. Now, do you see how the black line has these spikes? And sometimes the response time is much higher here than at a higher load. So clearly it's not just a function of load. In fact, the dominant behaviors in the response time don't seem to be a function of load, they seem to be a function of time. Some pattern, some amount of work done before you have to pay for it. Something like garbage collection pauses. Now, I don't know if this is GC pauses, it's just a graph. But I call these hiccups. Everything is fine except for rarely it's not, and that's the devastating thing that breaks the system. What JHiccup does is really simply measure those hiccups, and it does a really simple thing. It sees whether or not the computer can do nothing. How long it takes to do nothing. Wait a millisecond? Did it take longer than a millisecond? Well, I was supposed to run and I didn't. And it's simple. You can add it as a Java agent to any application, and it gives you graphs like this that show you that something in your computer froze for that amount of time at that point in time. It also plots percentiles of those freezes. And while this doesn't tell you what your application behavior was, the application behavior couldn't be any better than that. If this says that 99.9% of the time, or 0.1% of the time, you had blips that were at least 25 milliseconds, your application couldn't have done any better, because if it did nothing, it would have done that. So that's a tool that lets you measure things, and it's a way to see what's happening. If you want to play with it, you know, go ahead, and it's free to download and play with the source and hack it. These are examples of how we use it. The first thing I do is look at an empty system that does nothing and see if the system has noise in it. This is not the JVM's fault. If the system is idle and it has, which one? This is a quiet system. You know, it shows 1% busy, but blips of tens of milliseconds, and that's not garbage collection. That's just probably a cron job or something else taking the CPU. You can usually use that kind of thing to get your system to be very consistent within, say, half millisecond kind of noise, and then it's a good way to measure other noise. You can also use it for comparison of, or to look at graphs of different things. And it's a telco app that we've plotted. It's a financial services app. So that's, you measure stuff and you see what the behavior is, and knowing what the behavior is important in order to start dealing with it. Without it, the head in the sand thing is not very good. So how can we break through this wall? If we measure it, if we see it, what can we do about it? Well, we have to focus on the problem of basically decoupling scale from responsiveness. As long as scale and responsiveness are tied, we won't scale. And stop the world fallbacks, the stop the world pauses are the reasons people don't scale, so you got to get rid of them. These are three things that seem to be hard to do in garbage collection. We already talked about concurrent marking at rates that actually, keep up with CPUs. We talked about compaction and how the hard thing in compaction is actually not moving stuff, but fixing all the pointers, because you can't allow the application to see wrong pointers, so that's the problem. But this third one is actually really important. We talked about generational collectors, and they tend to be monolithic, stop the world. The only reason they're small in size is because the heap size are tiny. If I had a 100 gigabyte heap, my young generation live set and promoted set might be a gigabyte or two. That pause would be as big as the current biggest old gen pause that you have. The only reason it doesn't happen is you're not using memory, not using the scale of a $5,000 machine. So that also has to be solved. And solving them, that's just saying the same things in green, could get us to a situation where we can easily use the computers that we have. So I told you that I'll do the advertisement only at the end, right? This is where it starts turning into, aha, let's classify another collector. So the name C4 stands for the 4 C's in the title. It's a continuously concurrent compacting collector. And it has a concurrent, guaranteed single pass marker. That means that no matter how fast you mutate the heap, it will finish. It couldn't care less how fast you mutate the heap. It does not affect the marking situation. So it doesn't just work when you're running slow, it works at any rate that you run. More importantly even, it has a concurrent compactor. It can move objects without stopping you, and it can fix references without stopping you. And if you get to a reference before it, the reference gets fixed, and you don't have to wait for anybody to fix it. It's concurrent. It has a concurrent compacting old generation. It also has a concurrent compacting new generation. It's the exact same algorithm for both. Why do we have 2 generations? Because that's 20 times as efficient as having 1. We get much better CPU behavior, but we don't use generational to eliminate pauses. Both generations have exactly the same type of pause behavior. Most importantly, there are no stop the world fallbacks anywhere in the code. The code just doesn't exist to do it. It's the one thing that's causing people to not use memory. We took it out. So if you look at the algorithm, we use a new type of read barrier we call a loaded value barrier. There's an entire paper that describes how that works. I'll let you look at that if you want details. But a really simple way to describe it is every time we read a reference, we check to see if it's okay. And we do it using an extremely fast check. It devolves to basically a test and branch in the fast path. And the branch is always never taken. Well, 99.99999% of the time never taken, and if it is taken, you don't have to wait for anybody to fix it. And we use that one barrier to deal both with marking and compaction. So references that have not yet been visited, remember that marking race I talked about? So any reference that we didn't yet visit or guarantee will be visited by the marker has a state on it that says not marked through. It's different than the live or dead. It's not marked through in the reference. And anytime your application sees one of these, it's not allowed to see, observe, or use it without guaranteeing that that reference will be marked through. The way it does that is it puts it in a little thread local buffer of references to give the collector later and keeps going. It does one more important thing. It fixes the state on the reference, says it's marked through, and it also goes back to the place it read it from memory and stores it back there with a safe CAS. The reason it does that is what we call self-healing. It's the reason LVB is practical. If you run into something that needs fixed, that's the one time you'll run into that thing. It will get fixed, and you won't run into it again if you're doing a million-time loop over the same thing, and nobody else will run into it either. That means there's a finite number of these to fix, and the collector will get to most of them first, and if you get there first, you'll fix it and keep going. But they'll run out. You're not stuck on it. We similarly use the exact same logic to say if the reference points to an object that was moved somewhere else, we'll fix it. find out where it went, fix it, and you don't have to wait for anybody to do that. And then you fix it, you heal it, you keep going. And the last part is we have a very cool mechanism that uses virtual and physical memory mapping tricks to do hand-over-hand replacement of the memory. So we don't need 2x the memory for mark compact. We need 1 page of empty memory and we can compact the entire heap with it. Again, the technique is detailed in a paper. So what does that mean? What do you get as results? Well, this is out of an academic paper. So it's a logarithmic graph, because you don't do that other than academic papers usually. And it shows the worst case response time as the heap grows on the same workload. The workload here was a modified SpecJBB with a 2 gigabyte LRU cache that was churning very slowly. And as you can see here, ignore the green line for a second. The red line and the blue line are parallel GC and concurrent mark sweep. And as you can see, their worst case is pretty bad and gets worse as you grow the heap. Why? Because their worst case includes a sweep, and the sweep gets worse as you grow the heap. C4 is this purple line, and over here, it's not that good. That's that 1 byte in a gigabyte problem. You gave us, this is very little memory, and there's 2.5 gigabytes of live stuff, and you're allocating it 1.2 gigabytes per second. We're not that fast. We find the stuff, but we'll run out of empty memory before we find it, so you wait for that. That's why you see that response time. It's not a pause per se, it's you're waiting for the memory to be freed, and it's not there until it's freed. If you have enough empty memory, the efficiency grows to a point where the collector delivers empty memory faster than you consume it, and then you get this flat behavior. And that's the kind of behavior you want to see in a collector. Not sensitive peak, but anywhere in the range, it's roughly the same, and the problem is gone. By the way, the green line is, because it's an academic paper, and the academic paper was about the generational concurrent nature of this collector, the green line is C4 with generational turned off. It does achieve similar behavior, but it takes a lot more empty memory to get there because it's a lot less efficient. So that's what the difference between these 2 points are. Zing is a product that actually has this stuff in it. It's basically a JVM for Linux, and it gives you these kind of behaviors and numbers. But if you need to look at what it actually delivers, it lets you do what I call sustainable throughput. And sustainable throughput is not how fast can I run for a minute, it's how fast can I run while I meet my response time requirements and my boss is still not firing me for stopping for 2 minutes every hour. An example of unsustainable throughput is this. It's a really fast car. It doesn't go very far if you go really fast. So a way to compare throughput would be how fast can I go without crossing this line on response time, for example, without the percentiles going about this level, and this would be a regular, this is, by the way, Liferay portal load on some JBoss server, and running on the exact same hardware with CMS, you get a certain user load before you're about to cross this line. You go any higher on load, you go any higher on heap, you go any lower on heap, it breaks. With Zing, we get to do that on the same hardware. How do we get that nice flat behavior? We cheat. This is how we cheat. We use 50 gigabytes of memory, half the machine. The memory is there, it's cheap, we can use it, we can handle 10, 15, 17 times the users there and still go. That's kind of the benefit of sustainable throughput as opposed to I could go really fast between pauses. Visually, I really like this tweet. Do you guys know who Charles Nutter is? The JRuby guys? So when he saw JHiccup, this is what he tweeted. And he's right. That's why we built JHiccup. It lets you see how good our stuff is. So a way to describe that is Zing is on the left, regular hotspot is on the right. This is a 1 gigabyte thing in an 8 gigabyte heap. See how much better Zing is? Well, it's kind of hard to see until I highlight a few things. That's 12 seconds. That's 20 milliseconds. That's normalized. So that's kind of the benefit you get from eliminating pauses, and you can kind of show, okay, if you've got that problem, it's gone. So last part, and then I'm done with all this, solve GC for you kind of things. GC tuning. I told you I won't tell you about a lot of flags. Flags like these. Anybody recognize some of these? So this is the real world. This is what people do if they want to run applications that use a whopping 8% of a server with acceptable multi-second pauses. They still have to do all this to do it. And the interesting thing there is they'll have to use the right setting, and the right setting is different depending on, well, that's one application, that's another application. That may be 1 week, that may be the next week. Maybe you change the code, maybe you change the load. There are new settings that are needed. And sensitivity with settings is a bad thing, because you have to find that place where the collector promotes well enough but doesn't pause that often, is efficient enough, but the generational assumption is still there. You're mutating at a rate that the collector can keep up with. These flags actually control a bunch of those. The heap size, the new gen size. You've learned, hopefully, a bunch of mechanisms here, and you can use them to figure out what to move there. But we have a better way, and that's to learn how to tune Zing. So this is the complete tuning guide for Zing. There'll be a test at the end. Okay? This is how you tune Zing. You give us memory. And it's not that you need the memory. I don't know if you need 40 gig. But you give us 40 gig, it won't hurt. And once you have it working, you could chop it to 20 gig. Maybe it'll still work. 10 gig, maybe it'll still work. Keep chopping until it breaks, and then triple that and ship. That's tuning. Okay? And you don't have to search for the right setting. You're looking for this plateau, and once you find the place where it breaks, you need to stay far away from it. So find it, chop it down, and that's the one big thing you get to control, and that's it. If you're in the low latency world, you do a little more than that. You might have seen that we do stuff in very low latency stuff. So if you're in the low latency world, you do some tuning, but not too much. And assuming that you can do individual transactions today already that are short, and you don't have 1,000 threads competing for 3 CPUs, in your low latency world, you know not to do that, then you can usually get roughly a 10 millisecond worst case with Zing the day you turn it on. With some tuning, you could usually get to a worst case. I'm not talking average, I'm not talking mostly. I'm talking run this for 3 days, what's the worst you will see? And low latency apps, the ones that have more CPUs than threads and don't have scheduler contentions and all that, can get there. And we've had some people go below a millisecond. In fact, Martin Thompson blogged about a worst case 80 microsecond that he did with us. But Martin Thompson's crazy. I mean, he will pick that thread and nail it down to that core and send the interrupts to that core away from that socket and lock the memory down to this together and but you get some really good numbers. Most people don't like to tune that much and be that accurate, but you can get there. And mostly you could do that because the collector is highly concurrent. Now, Zing in implementation does have pauses. They're just super short, and they do no GC work in the pause. They tell the threads to flip states. We're starting to mark. Now run. We finished marking. Flip state, now run. We're starting compaction. Run. None of the work that has anything to do with scale, not the heap size, not the allocation rate, not the mutation rate, not whether you use weak references or soft references, not finalizers, none of those happen in a stop the world pause. And that's why we could get to these numbers. So we recently announced this thing. If you work on open source projects, you can actually use Zing for free for development tests and the rest. You can go to our website and see. And if you're interested in some reading about garbage collection, that's actual material out there. So, wow, I finished in 90 minutes. Amazing. So that's my talk. There's pizza and there's questions. You guys could just ask and eat at the same time if you want. I'm here as long as you want.